Greetings and welcome. This is an introduction to my procedural notation math syntax. This is an alternative to the 400-year-old PEMDAS legacy traditional syntax that people use. And this is based on CPU assembly language and elementary arithmetic as the basis for the structure of this notation. Computers don't do school board arithmetic. They don't know what a parenthesis is. They don't know what an equal sign means. They do what is referred to as assembly language. And this is a machine code. One operation, some parameters, and a repeated regular syntax. And it turns out this is a better way for humans to do math as well. It's not just good for computers, it's good for you. Let's take a look at something that would be a problem for a math student. What does this mean? As you go through your math levels, you discover this doesn't necessarily symbolically mean as clearly what you thought it did when you were first told it meant 2.5. When things are next to each other, they're supposed to be multiplying. But if you don't put parentheses there or a plus there, how do we know what that 2 is doing to that 1/2? Is it a value of 1 or is it a value of 5/2? That's a significant problem. That's a significant difference. If we just added a decimal point to concatenate the integer and the fraction, that would make more sense. But we don't do that because we do math the hard way. We are taught when we are young 2 different ways to do mathematics, and sadly, it turns out we follow the wrong path. And numbers were giving us a clue that we were doing it the wrong way. When you're starting your first elementary arithmetic and you're learning your basic operations, add, subtract, multiply, divide, they're not done in PEMDAS format. They're done in this vertical alignment where you can line up your decimal places, and that's how you learn to carry the 1 or subtract a 1 from the next column. That's the important part of getting math theory right, is understanding the numbers. And the numbers knew how to do it correctly. We just stopped using it after one operation. We only did add, subtract, multiply, and used a completely different shape for division, and there was no further extension in that format. Going further, you go into algebra, and everything looks effectively like a written statement. 1 plus 2 is equal to 3 is actually the origin of that equal sign. It was a shorthand for saying is equal to. And most languages in most societies are the origins of their math syntax. They did their written math in line with their linguistic syntax because that's the only application they had. And algebraic symbolic notation was developed differently and adopted different formats throughout societies. Now, both methods are accomplishing the same thing. They're performing a math operation, but they're expressing it in a different format. One of them has a positional control, where a division sign is a different shape than the add or subtract. They're not written in line unless you have to type it on a keyboard. And then even then, the numbers and the computer are telling you you're doing your math wrong because all symbols in math on the computer have to be entered as a symbol. So what if we just treated them all as symbols, and these hyper operations had a sort of equal syntax to each other and didn't look weird in strange conditions? Then maybe we would get rid of things like this non-ending internet meme of "I bet you can't do math." This is a tired old meme that is yet again another sign that perhaps we are not doing our mathematics properly. If so many people are getting this type of problem wrong, that perhaps means there's something that isn't intuitive and is easy to mix up. The whole point of a math syntax should be to express things clearly and consistently so that everyone gets the right answer. That is the whole point of a math syntax. If you're using software that allows you to type something in like this, What the software is doing is it's translating this input into something that functionally looks like this. It performs the operation in sequence, one at a time, and things like parentheses are subunits. They're subfunctions, little operations. And in a stack environment, a stack computer, we would call this pushing onto the stack a value of 1 plus 2, and then popping the stack when you're complete. In this notation, you can see multiplication and division are commutative, and we can move between the two. And you can see that at the end, we can even make parentheses disappear, because now that our vertical line is a sequence of time, we don't need parentheses or brackets or braces or whatever desperate curly shape you come up with to separate and denote your time sequences. Time is a vertical dimension and space is a horizontal dimension. And here we see a translation of one sequence to another to another. And so how does this relate to computer programming? Quite directly, into assembly language. Now there are some things that we as humans don't need to do. We do not need to move 10 into our x variable. We understand we're talking about 10, and we do not need to copy something in our head to do this multiplication. But here you see that the two multiplication operations, one to effectively perform the square and the other to multiply by 9, can be translated directly into a generic CPU assembly language. We're presuming R2 is our output. We're presuming R1 is our input. But that's just an arithmetic operation. Let's actually turn it into the algebra you see on the right and actually make it into something that accepts a variable. We can do that by describing a condition on the left where x equals 10. You'll see that that is the condition space. That is where you describe x has to not equal 0, or must be a member of some group, or must be greater than a different value. You can do all of your Boolean and or XOR not operators on the left-hand side, and they describe what is going on the right. So on this condition, I shall move myself, we have x squared times 9 is 900 in full assembly language and a mathematical syntax. That's unique and distinct from something in PEMDAS. You don't get to write this out in assembly in PEMDAS. There are also things that you can represent that can be obscure when using a traditional notation. I was reading an article, and after reading it 3 times, finally understood that they were not saying A and B and C are all equal. That was a misunderstanding. What they were trying to convey was that the concept of A equaling B is actually what we refer to as C, and I found that infuriating. In computer programming, we have a thing called a header, and this is a place where you can put comments, a description of the inputs, the signature. Each programming language has its own particular behavior with its signatures, but I've generally found there is no common accepted format to have a header to a function. This is a place where you would describe what types of inputs. You can put a small sentence, a synopsis of what does this subroutine or function do. What is it accepting? Arrays, real numbers, imaginary units, all of that could go where C is. And now you don't need a paragraph describing something and referring to figure B7. Your text, your descriptive text, could be attached to your actual formula. That would be an advantage in graphing and charting when you have to explain something and describe which component is being described. But if we go back to A equals B equals C, we can see here that it's easy to follow which operations are moving where, because all they have to do is cross one equal sign and they flip their sign. So addition would become subtraction, and we can even demonstrate going in multiple dimensions, which I truly doubt you would be able to represent in traditional PEMDAS, because these equal signs, these lines, can be drawn in any direction you want to go. If you run out of space and you need to word wrap, you just simply word wrap your line from one side of the page to the other, and there you can continue your formula and not have to worry about showing your work clearly. Your work is extremely clear. Here is balancing for A. I want to solve for A, and here I can simplify and go all the way to the end and see that it is easier to track what operation is going from what side to the other because they're all the same shape. They just have a matching sign, so subtraction becomes addition, and then beyond here the rest is simplification. So we're simply multiplying and adding numbers together. We can see that 5 and the 37 can be added together because there's just a subtraction between them. It's the same thing as addition in terms of our operations. And you do treat exponent and root different, but if you're just doing basic algebra, this is a much easier to follow set of work. And it is technically one equal sign and multiple timelines that share this equality. So now you've gotten to this part and you say, okay, there's nothing interesting or new here that I couldn't have done in PEMDAS. All of this is just yet another thing someone would have to learn. Well, I argue it's harder to get this wrong because you are doing the same thing, reading instructions out from top to bottom. But let's just say that was your argument. Well, here is something that you cannot do in PEMDAS that you can do in procedural notation in one step. Solve for A. In one step and show all work. It's a contradiction. You can't show all work in one step that far deep in that many operations. You'd have to rewrite the formula over and over and over in PEMDAS. But in procedural notation, time is a dimension. And so we can show all work by simply displaying which component becomes which other matching component on the other side. We're flipping our operations as they cross the equal sign. And here I have solved for A in one step, showing all work. Again, the timeline in PEMDAS is some sort of curve that would go through the letters or numbers. I don't know how to represent time in PEMDAS, but in procedural notation, it's very much a clear and distinct set of a sequence. And we don't have to worry about interpreting it or processing it. We just perform it as it's stated. So hopefully something in this presentation has piqued your interest, and I hope to hear some comments from the viewers. If there's anything you would like to cover specifically, I may be able to release some of those chapters soon. I'm doing the introduction to the syntax, the basics, and then the next section is actually the programming section that covers pseudocode representation, if statements, switch statements, loops, error handling. All of these are functional elements in this mathematical syntax, and I would love to see some requests and some feedback about what you think this could be used for. If you find it of help, please reach out and like and subscribe, and take care. Have a good one.